Minimax is a decision rule used in decision theory, game theory, statistics and philosophy for minimizing the possible loss for a worst-case scenario. Originally formulated for two-player zero-sum game theory, covering both the cases where players take alternate moves and those where they make simultaneous moves. It has also been extended to more complex games and to general decision-making in the presence of uncertainty. Game theory. In general games, the maximum value of a player is the largest value that the player can be sure to get without knowing the actions of the other players. Its formal definition is, where is the index of the player of interest, denotes all other players except player, is the action taken by player, denotes the actions taken by all other players, is the value function of player. Calculating the maximum value of a player is done in a worst-case approach. For each possible action of the player, we check all possible actions of the other players and determine the worst possible combination of actions, the one that gives player the smallest value. Then, we determine which action player can take in order to make sure that this smallest value is the largest possible. For example, consider the following game for two players. For the sake of example, we consider only pure strategies. Check each player in turn. The row player can play T, which guarantees him a payoff of at least 2. Hence, the column player can play L and secure a payoff of at least 0. Hence, if both players play their maximum strategies, the payoff vector is. In contrast, the only Nash equilibrium in this game is, which leads to a payoff vector of, the minimax value of a player is the smallest value that the other players can force the player to receive, without knowing his actions. Equivalently, it is the largest value the player can be sure to get when he knows the actions of the other players. Its formal definition is. The definition is very similar to that of the maximum value, only the order of the maximum and minimum operators is inverse. For every player I, the maximum is at most the minimax. Intuitively, in maximum the maximization comes before the minimization. So player I tries to maximize his value before knowing what the others will do. In Minimax the maximization comes after the minimization. So player I is in a much better position. He maximizes his value knowing what the others did. Usually, the maximum is strictly smaller than the minimax. Consider the game in the above example. The row player can get a value of 4 or 5, so the column player can get 1 or 4. Hence, in zero-sum games, the minimax solution is the same as the Nash equilibrium. The Minimax theorem states, for every two-person, zero-sum game with finitely many strategies, there exists a value V and a mixed strategy for each player, such that given player 2's strategy, the best payoff possible for player 1 is V, and given player 1's strategy, the best payoff possible for player 2 is minus V. Equivalently, player 1's strategy guarantees him a payoff of V regardless of player 2's strategy, and similarly player 2 can guarantee himself a payoff of minus V. The name Minimax arises because each player minimizes the maximum payoff possible for the other, since the game is zero-sum. He also minimizes his own maximum loss. This theorem was first published in 1928 by John von Neumann, who is quoted as saying, "As far as I can see, there could be no theory of games without that theorem. I thought there was nothing worth publishing until the Minimax theorem was proved." See Sion's Minimax theorem and Parthasarathy's theorem for generalizations. See also example of a game without a value. Example: the following example of a zero-sum game where A and B make simultaneous moves illustrates Minimax solutions. Suppose each player has 3 choices and consider the payoff matrix for A displayed at right. Assume the payoff matrix for B is the same matrix with the signs reversed. Then, the minimax choice for A is A2 since the worst possible result is then having to pay 1. while the simple minimax choice for B is B2 since the worst possible result is then no payment. However, this solution is not stable, since if B believes A will choose A2 then B will choose B1 to gain 1, then if A believes B will choose B1 then A will choose A1 to gain 3, and then B will choose B2, and eventually both players will realize the difficulty of making a choice. So a more stable strategy is needed. Some choices are dominated by others and can be eliminated. A will not choose A3 since either A1 or A2 will produce a better result. No matter what B chooses, B will not choose B3 since some mixtures of B1 and B2 will produce a better result, no matter what A chooses. A can avoid having to make an expected payment of more than 1/3 by choosing A1 with probability 1/6 and A2 with probability 5/6. The expected payoff for A would be 3 times minus 1 times equals minus 1/3 in case B chose B1 and minus 2 times plus 0 times equals minus 1/3 in case B chose B2. Similarly, B can ensure an expected gain of at least 1/3, no matter what A chooses, by using a randomized strategy of choosing B1 with probability 1/3 and B2 with probability 2/3. These mixed minimax strategies are now stable and cannot be improved. Maximine frequently, in game theory, maximine is distinct from minimax. Minimax is used in zero-sum games to denote minimizing the opponent's maximum payoff. In a zero-sum game, this is identical to minimizing one's own maximum loss, and to maximizing one's own minimum gain. Maximine is a term commonly used for non-zero-sum games to describe the strategy which maximizes one's own minimum payoff. In non-zero-sum games, this is not generally the same as minimizing the opponent's maximum gain, nor the same as the Nash equilibrium strategy. In repeated games, the minimax values are very important in the theory of repeated games. One of the central theorems in this theory, the Folk theorem, relies on the minimax values. Combinatorial game theory. In combinatorial game theory, there is a minimax algorithm for game solutions. A simple version of the minimax algorithm, stated below, deals with games such as tic-tac-toe, where each player can win, lose, or draw. If player A can win in one move, his best move is that winning move. If player B knows that one move will lead to the situation where player A can win in one move, while another move will lead to the situation where player A can, at best, draw, then player B's best move is the one leading to a draw. Late in the game, it's easy to see what the best move is. The minimax algorithm helps find the best move by working backwards from the end of the game. At each step it assumes that player A is trying to maximize the chances of A winning, while on the next turn player B is trying to minimize the chances of A winning. Minimax algorithm with alternate moves. A minimax algorithm is a recursive algorithm for choosing the next move in an n-player game, usually a two-player game. A value is associated with each position or state of the game. This value is computed by means of a position evaluation function, and it indicates how good it would be for a player to reach that position. The player then makes the move that maximizes the minimum value of the position resulting from the opponent's possible following moves. If it is A's turn to move, A gives a value to each of his legal moves. A possible allocation method consists in assigning a certain win for A as +1 and for B as -1. This leads to combinatorial game theory as developed by John Horton Conway. An alternative is using a rule that if the result of a move is an immediate win for A, it is assigned positive infinity, and if it is an immediate win for B, negative infinity. The value to A of any other move is the minimum of the values resulting from each of B's possible replies. For this reason, A is called the maximizing player and B is called the minimizing player, hence the name minimax algorithm. The above algorithm will assign a value of positive or negative infinity to any position, since the value of every position will be the value of some final winning or losing position. Often this is generally only possible at the very end of complicated games such as chess or Go, since it is not computationally feasible to look ahead as far as the completion of the game, except towards the end, and instead positions are given finite values as estimates of the degree of belief that they will lead to a win for one player or another. This can be extended if we can supply a heuristic evaluation function which gives values to non-final game states without considering all possible following complete sequences. We can then limit the Minimax algorithm to look only at a certain number of moves ahead. This number is called the look-ahead, measured in plies. For example, the chess computer Deep Blue looked ahead at least 12 plies, then applied a heuristic evaluation function. The algorithm can be thought of as exploring the nodes of a game tree. The effective branching factor of the tree is the average number of children of each node. The number of nodes to be explored usually increases exponentially with the number of plies. The number of nodes to be explored for the analysis of a game is therefore approximately the branching factor raised to the power of the number of plies. It is therefore impractical to completely analyze games such as chess using the Minimax algorithm. The performance of the naive Minimax algorithm may be improved dramatically, without affecting the result, by the use of alpha-beta pruning. Other heuristic pruning methods can also be used, but not all of them are guaranteed to give the same result as the unpruned search. A naive Minimax algorithm may be trivially modified to additionally return an entire principal variation along with a Minimax score. Pseudocode. The pseudocode for the depth-limited Minimax algorithm is given below. O1 function Minimax O2 if depth equals 0 or node is a terminal node. O3 return the heuristic value of node O4 if maximizing player O5 best value equals -infinity O6 for each child of node O7 V equals Minimax O8 best value equals max O9 return best value 10 else 11 best value equals plus infinity 12 for each child of node 13 V equals Minimax 14 best value equals min 15 return best value Minimax. The Minimax function returns a heuristic value for leaf nodes. Non-leaf nodes inherit their value, best value, from a descendant leaf node. The heuristic value is a score measuring the favorability of the node for the maximizing player, hence, nodes resulting in a favorable outcome, such as a win, for the maximizing player have higher scores than nodes more favorable for the minimizing player. The heuristic value for terminal leaf nodes are scores corresponding to win, loss, or draw, for the maximizing player. For non-terminal leaf nodes at the maximum search depth, a position evaluation function estimates a heuristic value for the node. The quality of this estimate and the search depth determine the quality and accuracy of the final Minimax result. Minimax treats the two players separately in its code, based on the observation that Minimax may often be simplified into the Nmnogueira algorithm. Examples: suppose the game being played only has a maximum of 2 possible moves per player each turn. The algorithm generates the tree on the right, where the circles represent the moves of the player running the algorithm, and squares represent the moves of the opponent. Because of the limitation of computation resources, as explained above, the tree is limited to a look ahead of 4 moves. The algorithm evaluates each leaf node using a heuristic evaluation function, obtaining the values shown. The moves where the maximizing player wins are assigned with positive infinity, while the moves that lead to a win of the minimizing player are assigned with negative infinity. At level 3, the algorithm will choose, for each node, the smallest of the child node values, and assign it to that same node. The next step, in level 2, consists of choosing for each node the largest of the child node values. Once again, the values are assigned to each parent node. The algorithm continues evaluating the maximum and minimum values of the child nodes alternately until it reaches the root node, where it chooses the move with the largest value. This is the move that the player should make in order to minimize the maximum possible loss. Minimax for individual decisions. Minimax in the face of uncertainty. Minimax theory has been extended to decisions where there is no other player, but where the consequences of decisions depend on unknown facts. For example, deciding to prospect for minerals entails a cost which will be wasted if the minerals are not present, but will bring major rewards if they are. One approach is to treat this as a game against nature, and using a similar mindset as Murphy's Law or resistentialism. Take an approach which minimizes the maximum expected loss, using the same techniques as in the two-person zero-sum games. In addition, expect to minimax trees have been developed for two-player games in which chance is a factor. Minimax criterion in statistical decision theory. In classical statistical decision theory, we have an estimator that is used to estimate a parameter. We also assume a risk function, usually specified as the integral of a loss function. In this framework, is called minimax if it satisfies an alternative criterion in the decision theoretic framework is the Bayes estimator in the presence of a prior distribution. An estimator is Bayes if it minimizes the average risk. Non-probabilistic decision theory. A key feature of minimax decision-making is being non-probabilistic. In contrast to decisions using expected value or expected utility, it makes no assumptions about the probabilities of various outcomes, just scenario analysis of what the possible outcomes are. It is thus robust to changes in the assumptions, as these other decision techniques are not. Various extensions of this non-probabilistic approach exist, notably minimax regret and info gap decision theory. Further, minimax only requires ordinal measurement, not interval measurements, and returns ordinal data, using only the modeled outcomes. The conclusion of a minimax analysis is, this strategy is minimax, as the worst cases, which is less bad than any other strategy. Compared to expected value analysis, whose conclusion is of the form, this strategy yields E equals N. Minimax thus can be used on ordinal data, and can be more transparent. Maximine in philosophy. In philosophy, the term maximine is often used in the context of John Rawls's theory of justice, where he refers to it in the context of the difference principle. Rawls defined this principle as the rule which states that social and economic inequalities should be arranged so that they are to be of the greatest benefit to the least advantaged members of society.